Hey guys, welcome to Unit 1 Notes B. Here we're going to focus on some important things to consider when we do the calculations in this class. The first thing is being comfortable using something called scientific notation. So here's an example of a number. It's a special number. You might recognize it. It's Avogadro's number. And it's always written in scientific notation because it's a really big number. Scientific notation is helpful in writing numbers that are really big or really small. Things that would have a lot of zeros either after them or before them. So there's a couple main parts. You have a number in front of the decimal here, and this number has to be between 1 and 9. For proper scientific notation, you can't have a 0 in front of the decimal, and you can't have 2 digits in front of the 0. So we're going to have to figure out where the decimal place would go in order to make it a number between 1 and 9. Then we would include all of our significant digits, which we'll talk about what that means in a minute. And then the next part of the format is times 10 with an exponent. Now this exponent is going to tell us everything else we need to know about the number. If it's a positive exponent, that means it's a really big number. And so that means that I would actually be moving this decimal place back 23 places to make this a very large number. If it were a negative exponent, that decimal place is actually going to then be moved towards me, or making it a very small decimal place, a lot of zeros before the actual digits. So we've got to figure out whether it has a positive or negative exponent, and then adjust our number to show that it's big number or small number based on positive or negative exponents. So this is going to be a better way to express big numbers or small numbers, where the large numbers have the positive exponents, and the negative exponents are for the small numbers or the decimal numbers. So let's try one here. This is a very large number, so we can tell it should have a positive exponent. But the first thing I need to figure out is where the decimal place actually goes. Remember, I want a number that's between 1 and 9. So I want to move my decimal place all the way up to behind the 1. From the understood decimal, that's all the way at the end. So that's going to move 3, 6, 9 places. So I'm going to write my 1 before the decimal place. I'm going to include the number up to the 7. Since these are just placeholders, I don't need to include them. So 0, 0, 7. And that kind of hits on the idea of significant numbers, which we'll talk about in just a minute. So 1.007 is my number before the times 10. And now I have to determine my exponent. That exponent represents how many places the decimal would be moved from where it really is to where we moved it to for proper scientific notation. And that was a change of 9. The last thing you have to determine is whether it's positive or negative. And since it was the large number, that would be the positive exponent. So I'm going to leave it as a positive 9. When you write numbers in scientific notation, you still include their units. So we want to make sure we don't drop the units. 1.007 times 10 to the 9th seconds. Now let's try one with a small number. When you have decimal places and you have a lot of them, it still helps to keep track of every 3 numbers, similar to the commas. But you can do that better after the decimal by using a space. You wouldn't have commas in a decimal place number, but typing that extra space can help you keep track of things. So that's just a way that you'll see things written to help us out. First thing I want to figure out over here is what number, what digit is the first one that comes between 1 and 9. Not double digit, just one digit. That 4 comes between 1 and 9. So that means my decimal is going to need to be moved to after the 4. It was originally way up here. So I'm going to move 3, 6, 9, 12 places to move it to where I want it for proper scientific notation. So I'm going to write my 4.76. If there were zeros after them, I would actually include them, just to give you a peek at that scientific notation thing. And then I'm going to write times 10. And now I need my exponent. How many places did I actually move? That was the 3, 6, 9, 12. But is that a positive or a negative 12? Well, since this was a very small number, my exponent should be negative, indicating that the decimal to get out of this would need to be moved to make it a very small number, a decimal. And then the last thing I want to do is make sure I have my units, my meters. So this would be 4.76 times 10 to the negative 12 meters. So notice that we have the negative exponent with the decimal as the intended answer. And when the number is really large, it's a positive exponent. It's positive exponent versus negative exponent. And then the other thing you got to be really careful of is that my digit in front of the decimal is between 1 and 9. No zeros, no double digits. And you will get dinged for using improper scientific notation. The trickiest part about using scientific notation are very large numbers, which does happen in this class a lot actually, is getting it into the calculator. So this is something that we're going to kind of have to work on together. What does your calculator look like? So a common button that we're going to see is a double E. You may also see EXP or times 10 to the X. Be careful, it's not just the 10x button that's by the logarithms. That's the wrong button. Times 10x. And I've also seen times 10n. So those would be individual buttons on your calculator that we need to find. So what we would type in for this example is the 5.02, and then we're going to type in that button. I'll just pick the first one. You got to figure out what your button is. The double E key, which, by the way, most of these show up as just a single E in the actual display, but it all means the same thing. And what it does is it represents times 10 and the caret to raise to the next exponent. So the next thing that I would need to type in here is the negative sign, which, careful, is not the same as the subtraction sign. The negative sign on a calculator is usually in parentheses, and then the 3. I have a habit of hitting enter way more often than I really need to, just because I have huge calculator trust issues with order of operations. So I would hit enter here, my 2 cents. But if you're using the correct scientific notation key, it does tend to help with order of operations. So you may not need to. Anyway, enter or not, and then hit your multiplication sign. Now we're going to type in our next number, 6.3369. And then here it's time for times 10 raised to a power. So I'm going to use that scientific notation button again, the double E key. And then I'm just going to hit my 5. So notice how this is a positive exponent. I don't need to type the negative, but I don't need to type the caret, the times, the 10. All of that is all wrapped up in this special button. And then ideally when you hit enter, you're going to get this 3,181. So I'm going to try to play with the way your calculator works. Do I need to type in maybe the exponent immediately after typing in the E key? Do I need to hit enter? Like, what are the little nuances of the calculator that you chose in order to be able to get the correct answer? So if you need help with that, please ask right up front, because we're going to be using scientific notation in the calculator a lot. So you want to make sure you know how your calculator works. All right, got it. All right, so now on to the next part of calculations. We're going to talk about something called significant figures. So I mentioned, like, when you're writing the scientific notation, leave off the decimals leave off the zeros that were just placeholders. So now I want to figure out what's a placeholder. What are zeros that matter versus zeros that don't? Or more directly asked, where do we round? How do you know when to cut it off? So the idea behind a significant figure is that significant things are meaningful. That kind of makes sense in English terms, right? Significant, meaningful means the same thing. So we only want to include numbers that actually carry meaning. Something that is actually measured would carry meaning. Whereas the placeholders, yeah, they mean something, but we can just throw it in scientific notation. We don't really need them. So the idea behind significant figures is to get rid of the stuff that we don't really need, that we could just use scientific notation for instead. So significant basically means it's reliable. And when it comes to labs and collecting our own data, we are kind of limited by the instrument or the tool that we're using. So for example, if you're using a scale and it has 2 decimal places, we would want to record all of our data to 2 decimal places. Why would we cut off numbers that the scale is giving us? But at the same time, we couldn't make up numbers beyond the precision of the scale. We couldn't make up a 3rd decimal place for our 2 decimal place scale. That estimation would not be reliable. There's nothing that's running off the screen to give us any indication of what a 3rd decimal place would be, and so we would be limited to the precision of the tool that we're using. Same thing with something that's not digital. We call it analog, like a ruler. The ruler only has markings to the 10th place. So how closely can we really round that? How many decimal place can you really estimate off of that? So the level of precision of an instrument can actually be something you can infer from the data that's provided. So for example, if I looked at 2 numbers, 3.50 grams versus 3.5 grams, I can actually tell that the first value was collected by a scale that was more precise or provided more decimal places than the other scale. Typically, when we're reading off of a digital platform, we just record all the numbers they give us. So for example, if the scale said 3.50, you would want to make sure you write down that 0. But there's also analog measurements that need to be made, or things like a ruler where you're trying to figure out where it lines up. Even math can be done this way with a triple beam balance. Maybe something like you've seen at the doctor's office where they have to move the scale back and forth to try to figure out what your correct weight is, or mass is, I should say. We have a certain level of precision that's indicated with that. And with analog measurements, you actually can estimate only one decimal place past the tick marks. So for example, I can tell the 3.5 grams had markings with 3 and 4, and that my value was actually about halfway in between. So it's one estimation. Whereas the 3.50 had markings up to the 3.5, 3.6, or going back to 3.4, it had markings to the 10th place. And I'm able to tell visually with my eyes that it actually hits 3.50 on the nose, that it hits that 3.5 marking exactly and isn't halfway down to the next marker. So we're actually making one estimation, only one. We would have no basis to go any more precise than that. But typically with an analog instrument, you can tell if it's hitting a marking exactly or if it's in between 2 markings. And so that's a justifiable estimation, but anything past that is not an okay estimate to make. Whatever these limitations are, whether it being the digital scale or the analog scale, whatever those estimations we're able to make from that, that's it. That's the only numbers that carry meaning, meaning those are the only significant figures. So whenever we use the significant figures to record data, we're going to limit or cut off our data based on the tool that we use. But that's not the only way to determine significant figures. So what we've been talking about for the last couple of minutes have been all about you recording your own data, your own measurements. But we're going to do lots of problems in this class where you're given numbers, given data, given worksheets, things like that. So how do you determine the number of significant figures in numbers that you're given? So the rule for that is actually called the Atlantic-Pacific rule. And I'm assuming you know this by now, but the Atlantic Ocean would be on the right and the Pacific Ocean would be on the left. And so that's kind of what's going to determine whether we're rounding or how we're rounding coming from the left or from the right. So the idea here is that if I have a decimal that's present, like 3.50, then I would start counting from the left-hand side. Whereas if I have a decimal that's absent, like 400, just 400, no decimal actually written, then we would start counting from the Atlantic side. And yes, I understand that there's an assumed 0 at the end. Assumed 0 counts as absent 0, right? Same thing. But if you actually write the decimal, then that counts as decimal present. This is going to determine what side of the number to count from. Once you start counting, you keep going. So the idea is you first find the non-zero number that you approach from whichever side, and then you would keep counting all the way to the very end of the number. So this is going to help us identify the placeholder zeros. This little trick, the Atlantic versus the Pacific rule. So let's see how this works in action. First, I have 3.00700. So here I see a decimal that's actually written on purpose, not an understood decimal, but a real decimal. So that means the decimal is present. So that means I'm going to count from the Pacific side, which basically means from the left side. And I want to find my first non-zero number, which would be that 3. So that means I'm going to count all of the numbers afterwards. So 1, 2, 3, 4, 5, 6, 6 digits. Once I start counting to the end of the number, means 6 significant figures. Now let's look at a number where the decimal is absent. I don't see the decimal. Yes, I understand it's at the end, but it's an implied placement. The decimal is absent. It is not physically written. So that means I'm going to start counting from the left-hand side. From the right-hand side. Because decimal absent means we're coming from the Atlantic, which would be on the right. And so the first non-zero number that I actually reached this time would be the 7. And then I would count all of the numbers past that. So that's just 1, 2, 3, 4 digits, or 4 significant figures. Notice how the zeros here only make sure that I'm in the 300,000th place instead of just the 3,000 place. So we call that a placeholder 0. Whereas here, this would actually indicate the level of precision of a tool. I had a tool capable of measuring to this place, and I can tell I hit it on the nose. Well, that carries meaning, and so therefore those zeros are significant, as opposed to just being placeholders. We can get rid of placeholders using scientific notation, so that's how we can determine whether the numbers are significant or not. If you need the numbers when you write it in scientific notation, then they are significant. So if we actually measure these numbers, we want to make sure we include them when we write our numbers. All right, let's try a few different things with significant figures. So the first thing I want to do is get good at counting the number of significant figures. So I want to go through these 3 examples and determine how many significant figures there are using the Atlantic or Pacific rule. First one, decimal is present, meaning I'm going to come from the Pacific. I'm going to go through all placeholder zeros, stopping at the 3. Once I determine where to stop, I continue to the end of the number, meaning that 0 is actually significant. If there was decimal absent, I would cut off that 0, but there's not. Decimal present, I measured that 0. The scale, or I shouldn't keep saying scale, but whatever the measurement is, in this case volume, actually had markings to this decimal place, and so I can tell from that 0 that it hit it on the nose. It's meaningful. So I have 1, 2, 3, 4, 5 significant figures. Now let's look at the second one here. I have no decimal. Commas don't count. No decimal physically written, which means I'm going to come from the Atlantic over here, meaning the first non-zero number I reach is the 9. So that's going to include 1, 2, 3 digits, or 3 significant figures. And then the last one, we have, again, no decimal places, understood decimal. So that means I'm starting at the Atlantic, decimal absent, but I actually hit this 1 right away. So that means all of these numbers are significant, all 10 of them. Now, if that number 1 was a 0, I'd fly right through them and have only 1 significant figure. But whenever the zeros are trapped like they are here, in between actual digits, then the zeros will always be significant. Zeros in front of a decimal or after a large number, placeholder zeros. These are your ones that are not significant and don't count as significant figures. So we have 5, 3, and 10. Now, we're going to do a lot of calculations in this class. And the thing is, we have to round our final answers to the proper number of significant figures. So say we type some math calculation, something in the calculator, and we get these large numbers with all these decimals. But we know, with rules we'll go over in just a few minutes, that the final answer should have 3 significant figures. How do I round these numbers down to having only 3 significant figures? So let's start with the first one. 366.2. My beginning numbers are the ones that I want to make sure are significant. The following numbers need to either become placeholder zeros or get rounded off. So in this case, my 6 is the last digit that I want to actually write down. And so I just need to determine, would the 2 make the 6 round up or down? And it would round down or stay the 6. And so the answer is this 366 liters. If that 2 was above a 5, I would change that to 367 liters. So it's very similar to rounding that you've been doing already. You just have to know where you're rounding. The next one is a little bit trickier because it's a much bigger number. So again, I'm going to start off with that I want these first 3 digits. And I want to think about what the next number does. Does the 7 make the 4 round up or down? And it will make it round up because it's above 5. So I'm going to write 905. But the problem is, this number represents 9 million, and that just says 900. So how can I actually make 9 million be present with only these 3 digits or these significant figures? And the trick is you have to turn all of these numbers into placeholder zeros. So I'm going to include 4 more numbers as zeros so that that 9 moves from the hundredths place to the millions place. Much rather have $9 million than $900. So we don't want to change the number when we round it. We want to keep the placeholder zeros. This follows the Atlantic Pacific rule because with no decimal, I would only have the 905 as significant. And I would go right through those other zeros. Then I would want to make sure I include units, of course, milligrams, and I have my final answer. The other option I could do is write this in scientific notation, 9.05 times 10, and then consider where I would have to move it. In order for 9 to be the digit, I'd have to move it 6 places. So either of these would actually be fine, writing it in scientific notation or using the placeholder zeros, whatever you're more comfortable with. But you do have to represent that it's 9 million, not 900. All right. Last one is super tricky, and every year it takes a little bit of time and maybe 1 or 2 kids can figure it out. So what do you think we should do if it's 999.9 and I want to round it to 3 digits? Well, the 9 would make the 9 round up, right? And so this basically should round up to 1,000. But how many significant figures does 1,000 have? Well, if decimal is absent, then it only has 1 significant figure. It is possible, although it makes everybody uncomfortable at first, to put a decimal at the end of a number without a subsequent decimal. That would just indicate a level of precision to the tens place. So if I do that, I would consider decimal present, and I would now come from the Pacific, but that would have 4 significant figures. So with or without the decimal, 1,000 doesn't have 3 significant figures. There's actually only one solution, and that is to use scientific notation. So you can use scientific notation to force the correct number of significant figures, using the 3 to represent the other 0 or the other placeholder, but only including 3 significant digits, 1.00, and the number used for the scientific notation. So it's kind of a cool little trick. Whereas for this one, it didn't matter which one you used. Sometimes if you can't get the number to have the correct significant figures, scientific notation is the only answer. So it's good to be comfortable with scientific notation. It does come up a lot. All right, now I mentioned that you may have to round to certain specific significant figures, but how do we determine what those significant figures are? How do you know that you need to round to 3 significant figures? Maybe it's 5 significant figures. How can you determine that? So there are certain rules, and it all has to do with what kind of mathematical operation was performed. So the rule for multiplication and division is that you would always round to the least number of significant figures from all of the components that you were multiplying and dividing. So for example, here I have 23.0, 432, and 19. So the first thing I need to determine is how many significant figures in each one. Here I have decimal present, so coming from the Pacific, I get 3 significant figures. This is decimal absent, but there's no zero, so of course that's 3 significant figures. And then same thing here, decimal absent, so they're both significant, but this one only has 2 significant figures. So it's 3 versus 3 versus 2. Which one is the least? And that would be 2 significant figures. So if we type this into the calculator, we get this big number, this run-on answer. We want to round the first first 2 digits, because the least number of significant figures is 2. But you do want to check the next number over. Is the second 8 going to make the first 8 round up? And yes, it's greater than 5. So you can see here we've got 19 instead of 18, but the rest of these numbers became placeholder zeros. So that way I come from decimal absent and only have the 2 significant figures in my final answer. So for multiplication and division, you would go by the least number of significant figures. All right, but there's a different rule if you're doing addition and subtraction. When you're going through addition or subtraction, you would go by the least number of decimal places. So here's another example. In this example, we have 123.25. So here I have 2 decimal places. 46.0, where I have 1 decimal place. And then this 86.257, I have 3 decimal places. So the least number of decimal places is actually 1 decimal place. So I get my long answer here, but I want to round to where this 5 is. And the 0 does not make the 5 round up, so it's just 255.5. And we stop there. Notice that we're not limited to sig figs. Like this would only be 3 sig figs, and this one ends up with 4 sig figs. Sig figs don't matter when it's, well, I shouldn't say they don't matter, but the number of significant figures don't drive the number of significant figures for their answer when you're doing addition and subtraction. You've got to look at the number of decimal places and the decimal places only. And actually in this class, we do like 10 times more multiplication and division than we do addition and subtraction. So this rule gets forgotten usually by the time we need it. So remember, addition and subtraction goes by decimal places. It is different than the multiplication and division. All right. So let's practice a few calculations, and this is actually going to give us a little bit of practice with how units work as well. How to derive units, or how to get units that come from other numbers. So first, I have 36.57 meters divided by 3.21 seconds. So I'm going to go ahead and punch that in my calculator. 36.57 divided by 3.21. And I get 11.39252336. And the calculator just goes on and on. What we have to determine is where to round that. So this is multiplication and division. I'm going to go by the least number of significant figures. So here I have 4 significant figures versus 3 significant figures. So the least number is 3 significant figures. So I'm going to keep 1, 2, 3 digits. But we do have to check, would the 9 round up to 3? And yes, it would. Not 11.4. Now, usually when you have a unit on the top and a unit on the bottom, if they're the same, they cancel. But if they're different, they don't cancel. So I just have meters on top and seconds on the bottom, and those are my units. So that's what we call a derived unit, something that just comes from using two different pieces of data, two different types of data. The length per second, meters per second, how fast something is going, or velocity. All right, let's look at the next one. Here I can see addition. So I can tell I'm looking at decimal places. So let's first type the number into the calculator, or the problem into the calculator. 41.376 plus 13.3 plus 42.9. Oops. Calculator error, my apologies. 42.9. And we get 97.576. And then the question is, where do we round? Well, here I have 3 decimal places. Here only 1, and here only 1. And when we do addition, we go by decimal places. So I can tell I want to round my number to only 1 decimal place. Does the 7 round up the 5? It does. So it's 97.6. And then when you add, the units actually have to be the same, and then they just stay the same. So that would just be grams. All right, next one is multiplication again, similar to number 1. So we're going to be going by this least significant figures. So I'm going to type in 5.67 times 13.44, and I get 76.2048. But I need to determine where to round. So first number has 3 significant figures, and the second number has 4. And because I'm doing multiplication and division, I want the least sig figs, so I need 3. So it's the 7, the 6, and the 2. Now would the 0 round up the 2? No, it would not. So I'm just going to round those out. But the units are a little bit different this time because I'm multiplying like units. So a meter times a meter is meters squared. So 76.2 meters squared. All right, on to some division and then secondary division. So I want to be careful about how we type this in the calculator. 5.83 divided by 2.67, because that's in parentheses. I want that to process first. I'm going to hit enter, and then I'm going to hit divided by 2.1. And so my final answer is 1.03977, and it actually continues on from there. Since I'm doing division, I want the least number of significant figures. So my first factor has 3 significant figures. Second factor has 3. And then my last factor actually only has 2. So I just want the 1 and the 0. Now, does the 3 make the 0 round up? No, it does not. So we're going to round that off. But don't round off the 0. That's there on purpose. That's our second significant figure. Now, the units on this one can be a little bit tricky. So I have meters per second. That's not a good place to write it. Let's try down here. Meters per second divided by another second. So whenever you have a fraction in a fraction, to solve that, you actually need to use something called the reciprocal. So we can put seconds over 1, because dividing anything by 1 doesn't change it, right? So this is meters per second over seconds over 1. Now to get the fraction out of the fraction, I'm going to flip my denominator. So it's like multiplying by 1 over second. And that's going to get rid of fraction in fraction. And then what happens is we multiply across. And the only thing on top is meters. But on bottom, second times second would actually be seconds squared. So my unit for this one is meters per second square, a unit for acceleration. So we're going to use our reciprocal whenever we have fraction in a fraction. All right, last one here. We have 9.374 times 6. So let's go ahead and put that in. So I get 56.244. And then we've got to determine where to round. So I again see the multiplication, so I want to go by significant figures. In the beginning, I have 4 significant figures. This last number only has 1 significant figure, which means I'm going to round this all the way to just that 5 position. Now, does the 6 make the 5 round up? Yes, it does. So this 56 is actually going to round up to 60. And then as far as units go, if I were multiplying like units together, I would have squared, like we did in the middle here. But this is just volts times nothing. So the volts would still be singular, 60 volts, or V for volts. So that's our kind of practice with some of these problems, going through where to round and how the units work, so that we can handle these calculations. 11.4 meters per second, 97.6 grams, 76.2 meters squared, 1.0 meters per second squared, and then 60 volts, final answers. So from now on, any calculations that we do, we're going to round to the correct significant figures. We're going to follow the limitations presented by the tools, presented by the data. All right, now the last part of the notes for notes B, we're going to talk about how to convert numbers. And yes, we're still going to apply the scientific notation or the significant figures rules as we go through these conversions. Now let's get to the actual math calculations. So dimensional analysis is the name for a process used to change one quantity from a different quantity. For example, if I have 3 hours, how many minutes is that? If I have 10 pounds, how many tons is that? How do we convert from one unit to another? So the process itself is called dimensional analysis. In order to convert, here's another example, 60 minutes, that would be equal to 1 hour. We're going to actually be able to use these things that we know are equivalent to help convert other things to see what their equivalency would be. The key concept here is that your conversion factors use different units that are equal to each other. So for example, if you try to use a conversion factor that said 60 minutes was equal to 2 hours, of course you're going to get the wrong answer. You have to use different but equal measurements in order to convert some other units. So it's kind of a 4-step process. The very first thing that you want to do is identify the given information. So sometimes this requires looking through a word problem and trying to determine what you need to convert out of. What do I need to change? So if I was asked to convert meters to millimeters, meters would be where I want to come from, and that would be my given. When we start actually setting up these problems, we're going to start with the given. We're going to set that up first, where our given is, and that's going to determine the placement for all the other factors. The factors are going to be set up based on where to put them for a canceling process to occur. So say the given is A for apples. Then we would want to convert that to B for bananas. Well, what we would do is put apples on the bottom so it cancels, and put bananas on the top, so that's what we end up with. And that's assuming we have a conversion factor for how many apples equal bananas, which that's not really how it works, but just to give you the idea of whatever you start with goes to the bottom. And this could keep going. Say I didn't want to be in bananas. Maybe I wanted to turn it into oranges. So then I would put bananas on the bottom, oranges on top, and I could keep going. And you can chain these conversion factors up so that they connect and constantly cancel top to bottom until you get what you want. So we call that our conversion map. And I typically set up this map with units first and then go back and plug in the numbers. So that's our conversion factor. All based on what cancels. Once we get the map all set up, it's time to fight with the calculator. Get it in the calculator using multiplication on the top and division on the bottom so that you get the correct answer. Making sure your units cancel so that you end up with what you were trying to convert into, and you cancel out everything that you used along the way. So we want to make sure that we do that calculation in a way that makes sense. And then with any math, of course, the last thing that you should do is recheck your process. Recheck the answer makes sense. Did the units that you got in the end actually answer what the question intended in the first place? And did everything else actually cancel? So we're kind of looking over that map to make sure that it all makes sense. All right, let's put this process to the test. So first thing I want to do is convert 6 feet into inches. So 6 feet is where I'm coming from. That is what I'm going to start with as my given. I have a habit of putting the given over 1 in order to keep it in the numerator, because numerator versus denominator is kind of the crux of this. We want to make sure we know what's on top and what's on bottom. So something on the top would automatically go to the bottom. So this idea here is whatever I'm starting with, go straight to the bottom. Dimensional analysis 101. That's like an automatic. Anytime I want to convert out of a unit, it goes to the bottom. Now, what do I want to convert into? That would be our inches. So how many feet in an inch? And because inches is actually what I was looking for in the end, I don't need to go any further. So this is actually just a 1 conversion factor conversion. So now that I have my unit set up so that feet cancels with feet and inches is left and therefore will be present in my final answer, I can plug in my numbers. I know my map works. So how many inches are there in a feet? There are 12 inches per foot. So now to solve step 3, 6 times 12 is actually 72. So I would have 72 inches. But now let's think about significant figures. We can't end up with an answer that's more precise than the given information. So if the given information only has 1 significant figure, I can't end up with an answer that has 2 significant figures, meaning I need to round this to this 7 position. Now, does the 2 make the 7 round up? No, it doesn't. So with correct significant figures, this would actually be exactly 70 inches. So yes, 72 in math, but that's assuming it's 6.0, which we don't know. So we have, all we know is whatever it is would round to 70 inches. Final answer with correct significant figures with units. All right, let's look at another example. In this one, we're going to use some kind of weird made-up units and equivalency so that we can really test the process. So this is given that we have 5 bananas equal to a bundle. Think of that as like 60 minutes equal to an hour. And we have 10 bundles equal to 3 boxes. So again, that's just an equivalency. How many boxes are equal to 6,000 bananas? So it's the 6,000 bananas that I'm trying to change. So that's what I'm going to convert. That's going to be my given. So I'm going to start there. 6,000 bananas over 1. And then the very first thing I'm going to do is put my unit to the bottom. Whatever I'm given goes on the bottom. That's the only way to make it cancel. So now what I was trying to convert to was boxes. The problem is I have bananas equal to bundles and bundles equal to boxes. So I don't have anything that tells me how many bananas are in a box. So we have to first go from bananas to bundles before we can then convert bundles to boxes, which means now I'm going to need a second conversion factor. So in this case, I'm going to put bundles on the bottom and boxes on the top. My next conversion factor allows me to connect bundles to boxes. So I have bananas top to bottom, which will cancel, and bundles top to bottom, which will cancel, leaving me with boxes. So my final answer will be some number of boxes. Anything that doesn't cancel is in the final answer. So that's part of step 4 is checking, does that make sense? Were we looking for boxes? Did everything else actually cancel? My bananas and my bundles do cancel, and all that's left is boxes. So I know I've had this setup correct. So now it's just a challenge of getting the numbers in the right places and putting it in the calculator. So first, bundles to bananas is our first conversion factor, where there are 5 bananas and 1 bundle. Then the next one comes from this bundles to boxes. I have 10 bundles to 3 boxes. So taking that ratio from the actual question. A lot of times the ratios are things you already know, such as how many minutes are in an hour or they're things that you can look up, like how many inches are in a foot. But here we have a question giving us kind of derived equivalencies so we can test the process. And yes, you can expect stuff like this on your test, where we're trying to make sure you understand the process itself. All right, calculator time. What is 6,000 divided by 5, see how that's in the bottom, times 3, because it's on the top, and divided by 10, because it's on the bottom. Now, yes, you can multiply across and then divide at the end, but really watch your order of operations. It's probably one of the most common ways I see like the wrong math, where you have the setup correct, but then get the wrong answer. So I'm gonna type this in as 6,000 divided by 5 and hit enter, then times 3 and hit enter, then divided by 10 and hit enter. And so I get 360 boxes. Now, is this the correct significant figures? Not this time. My given information only had one significant figure. No decimal, decimal absent. It's coming from the Atlantic. I have one sig fig. So then the question is, what's 360 rounded down to having only one significant figure? Well, the 6 will round up to 3. And so this should be 400 boxes, rounded to one significant figure. All right. So we get our bananas to cancel, our bundles to cancel. We have our answer in boxes, and then we round to one significant figure. And we have our final answer. All right. The last problem I want to try actually has 2 units in it. So this is going to have us kind of think about how do we really get things to cancel. So the main idea was when we started on the top, we put it on the bottom to cancel. Now we're also going to have to think about what if we're given something on the bottom? How would we make that cancel? So let's look at this one. We are converting 25 meters per second to miles per hour. So the given is 25 meters per second. 25, the symbol for meters is M, and for second is S. So just like you've maybe seen miles per hour, meters per second, we could write kind of like this, or grams per milliliter, just indicating a division. Now here's the problem with that, is this looks like the second is in the numerator, when we know darn well it belongs in the bottom, it belongs in the denominator. This indicates that I'm going 25 meters per second. For every second that passes, 25 meters is covered. So this should be set up with the seconds intentionally in the denominator. And that's huge in terms of setting this up correctly. So never use the slash when you're doing dimensional analysis. Meters on top, second on the bottom. And by the way, how many seconds? When it's per second, that implies 1 second has passed. So I have 25 meters for each second, or for each 1 second. Now the first thing that I want to do is convert from meters to miles. So meters, we would want to put on the top in order to convert towards miles. So I want to put something up here that maybe has to do with going from meters to miles. I need to figure out what my conversion factors are. So for example, you could do from meters to kilometers, and then from kilometers to miles. There are also pathways where you go through yards, lots of different ways to convert meter to mile, and they all work as long as you're using valid conversion factors. For example, not using 2 hours per 60 minutes or something like that. As long as you have correct conversions, you're going to be able to get from meters to miles. Now for the new part. How do I get out of seconds? Well, if I put meters to the bottom to cancel when it's on the top, if I have something on the bottom, I would need to put it on the top to cancel. So if I have seconds on the bottom, I now need to put seconds on top. And I can go, I'm trying to go from seconds to hours, so I'm looking for a larger unit. I want to go from seconds to minutes, and then from minutes to hours, getting larger. So seconds would cancel with seconds. Actually, let me use a different color and just kind of show this. Meters top to bottom, kilometers top to bottom, still in miles, so my answer will have miles on the top. Then seconds, bottom to top. Minutes, oops, didn't set that up right. Minutes, bottom, so minutes on top. And then hour on the bottom. So my minutes now will cancel, bottom to top, leaving hours on the bottom. So hours will be on the bottom in my final answer, meaning my final answer would then be in miles per hour. Once you know your setup is good, you can go ahead and plug in your numbers. For example, 60 seconds per minute, 60 minutes per hour, 1,000 meters per kilometer. I don't know miles to kilometer off the top of my head, but I have it on the PowerPoint, so let's give it a second and we will pull up the math here. So, of course, they used a different conversion. So meters to the bottom, yards to the bottom, leaving us in miles. So slightly different equivalencies. The way that I had set it up would work too if I just knew my meter to kilometer. I'm sorry, it was the mile to kilometer conversion. Seconds, notice, looks the same up here, minutes to minutes, and we get 55.935 miles per hour. Now the catch is the sig figs, right? We've always got to check that our answer doesn't end up more precise than the given number. So the given number only has 2 sig figs, 25. So I want to round this 5. Now does the 9 make the 5 round up? Yes, it does. So with correct sig figs, this would actually be 56 miles per hour. Final answer. So the catch here is when you start with a unit on the bottom, you actually have to bring it to the top, and that's our challenge. All right, last thing that I want to mention, you may recognize this with the metric prefixes. Typically in middle school, they teach you how to kind of memorize how many decimal places to move based on some kind of King Harry acronym to know like how many steps, how many place values there are, which is great and all, but you can also use dimensional analysis like I just did when I was showing how to convert your kilometer and meter. So it's another way to convert things without having to memorize how many decimal places to move one way or the other. So it's also very useful to convert metric measurements. So just something I wanted to mention at the end here. So we've gone through a lot today. We've talked about 3 important things: scientific notation, significant figures, and dimensional analysis. So take some time to review all of these calculations because they will be very important going through this entire course. The next set of notes that we're going to look at are Unit 1, Notes C, where we're just going to talk about some basic matter classifications. So we'll see you there.